Here we are for this last presentation of this series of webinars, which was going through all the wavelengths. So today we are going to speak about the long wave infrared. So please come with me to this one. But first, again, you know me, I am Mathieu Marmion, working at Specim as a lead application specialist, and I'm really happy to be with you today again for this last session about our journey through the wavelengths. The agenda today. We're going to speak briefly again about the Specim company, who we are, how we have been created, things like this. What is long-wave infrared hyperspectral imaging? This is actually the highlight of the day. Applications and benefits about long-wave infrared. So I will go through some applications which use mostly this spectral range or combined with some others, but still. Specim offering for long-wave infrared, because to speak about it is nice, but if we have something to offer, it's even better. And actually, we have the camera just next to me here. Illumination requirement for this spectral range, because you can imagine this is a thermal range, so you cannot use typical halogen, things like this. So here we have actually a dedicated illumination. And finally, question and answer session. First, about Specim. Specim has been founded in 1995 and is a spin-off of VTT, which is a Finnish National Research Center. Since the creation of the company, we have delivered more than 10,000 spectrograph or cameras, let's say hyperspectral system all around the world. We have a annual growth which is about 20%, and since 2020 we are part of Konica Minolta Group. We are located in many places. The headquarters is in Oulu, Finland, and then we have offices all around the world in the United States, also in Spain, in Germany, and in China. In countries where we are not present ourselves, also where we are present, we have some distributors, so we have a network of distributors worldwide. So let's speak now about the topic really of the day. What is long-wave infrared hyperspectral imaging? First, hyperspectral imaging, as you start to know by now, this is a combination of spectral information and spatial information. From the spectral information, you can make some analysis, qualitative, quantitative, meaning sorting A from B from C, or to know what is the level of a variable of a characteristic, for example, moisture, in a sample. You can also play with color coordinate, but that's not with the topic of the day really. This is not the main application for long-wave infrared. Anyway, chemometrics, everything about analysis, spectral analysis can be done with hyperspectral imaging, identification and classification. But then, remember, this is an image. For each pixel, you get spectral information. So you can see also the distribution of something. You can see the size and the shape of something. You can make distribution statistics. So from that, you can make the combination of identification, classification with the distribution and areal separation. So this is actually hyperspectral imaging. At Specim, we have a wide offering like this of hyperspectral camera covering the full spectral range. So we have VNIR camera, as you know, we have NIR1, shortwave infrared, middle wave infrared, and today we're going to speak about the long wave infrared, and with the FX120 that we just launched recently, we can cover the spectral range between 7.7 and 12.3 micrometers. Now let's speak a bit about applications that can benefit about this camera, this spectral range. And this, I will speak about four main subset of application, but be aware that there are much more than that. So geology is one, geology and related, safety and security, environmental analysis, as well as detecting anomalies in a thermal way. First, about geology and mining. Drill core scanning and mineralogy, so mapping of different types of minerals, is one of the main applications that benefit actually from this spectral range. There are some minerals that could be identified only with this spectral range, for example, quartz, feldspar, and carbonate. It could be used as well for geological mapping in general, not only like for mining mineralogy, but also in geological mapping, and so volcanology. So what I was mentioning about the mineral identification, we have this table which has been made by Phil Harris. Thank you, Phil, for providing this table, where actually different type and group of minerals have been measured and try to be identified and characterized with different spectral range. So here you can see the VNIR, which is between 400 and 1000 nanometers, the SWIR, which is between 1000 and 2500 nanometers, and then the topic of the day, the long wave infrared between 8 and 12, in our case 7.7 and 12.3 micrometers. And as you can see, for most of the minerals, actually the long wave infrared is able to separate and to identify those minerals, highlighting that this camera is very, very suitable for core logging analysis and geological mapping. Also, it's relevant to combine long wave infrared with some other wavelengths. And here you have an example, for instance, of data fusion between VNIR imaging, here between 400 and 1000 nanometers, shortwave infrared, which gives some information about some minerals, but not all of them, but already with VNIR and shortwave infrared, you can make some nice identification, and those could even be refined or even improved in a way that new mineral could also be seen with the long wave infrared. And here you can see the different type of minerals and the mapping and the identification. It could be used as well like this, for instance, for airborne application. Here is an example of a map which has been done. To the best of my memory, it was in Nevada. But anyway, a courtesy again from Spectral Atlas, where you can see that a camera between 8 and 12 micrometers, basically hours, has been flown over an area, and then different type of minerals have been identified. And you could see, for instance, that the quartz, different type of quartz has been mapped, where normally the quartz could not be really identified with other spectral range. So here again, this nice application. By the way, keep in mind that hyperspectral imaging is a surface measurement method. So if over the ground you have vegetation or things like this, of course you cannot make mineral mapping. You see only what you have at the surface. So here it needs to be a bare ground. The camera could also be used for soil disturbance anomalies. So here you can imagine we have an area, the camera has been flown, and if you want to detect if something has been buried, for example, grave or explosives or different type of things just buried in the ground, you can then see here with this camera if the soil has been disturbed. If you have at the surface something which should be at the bottom, for instance, or something which should not be present in the area. Here again, this camera could be used for that. It could also be used with, for instance, between 400 and 2500 nanometers. It really depends on where you are flying, which type of mineral, which type of soil you are having in the area. It could be used as well for military application, like here, camouflage detection, because you know, typically camouflage materials, they mimic really well the color, but it has an issue to mimic really well the material. And here, the good thing with this camera is that it can detect different type of material. The second good thing is that this camera could be used even if you don't have sunlight. It could be used at night, because the other wavelengths, especially between 400 and 2500 nanometers, if you have the sample which is at room temperature, you see only the reflection from the sun, but it doesn't really emit from the background. You cannot really see that. But with this camera, you can fly at night and you can detect these kind of things. Could be used as well for gas detection. And actually here, this is very important slide that I would like to explain a little bit more. You can see the area, you have two men and you have then a background. It was like a bit cold outside. But what is interesting is to look at the four spectra that we are having. First, if we look at the white one, which corresponds to a warm background. So here this is the head of our colleague, and you can see the white background. The warm background is having the white spectra, which is giving actually the reference. Then the gas was colder actually than the head of a human, and then you could see the transmission through the gas, and this is actually the red spectrum. And here you could see how it differs from the warm background, and you can see basically the transmission of the gas, or let's say like the transmission, let's say you could see the absorbance peaks. You can do the other way. With the cold background, which is the sky, you could see that you have here the yellow spectrum, which gives you a reference, and then again with the green spectra, you have the gas, this time emission, because it's warmer than the background, and then you can see basically how the green spectra differs from the yellow one. So the red one corresponds to the transmission, and the green one corresponds to the emission, and you can see that actually it matches. Why? Because when something emits at a wavelength, it's actually absorbed at the same one or transmit. So here, this is a good example of how a thermal camera could be used here as well for gas detection. Thermal anomalies, that's the next level of application. It could be used for ground and water temperature mapping, heat mapping, volcanology, hotspot detection, lava dome and flow, especially now, you know, we are discussing a lot or talking a lot about this eruption of volcanoes in Iceland. So that's actually just on the topic now. Geothermal field, those are the applications. And here again, you could see two examples of temperature of solid and liquid target, like to make some heat map. On the left-hand side, a thermal camera was flown over a city area. So you can see here that it's possible to extract from the hyperspectral data, from the radiance data, you can extract Planck curve somehow, like you can try to match, and then you can deduce what is the temperature of your sample or of what you are looking at. And it could be used as well on the right-hand side, again, a courtesy from NERC. So there it was flown over a mining area, and you can see that you can map pretty accurately the temperature of different type of material, liquid bodies, and also solid ones like rocks. Environmental analysis, here the camera could be used for different type of identification of land cover type recognition, contamination and spill assessment, water quality, wetland management, vegetation classification and mapping, especially also you can look at vegetation stress and disease mapping, ecosystem analysis and evapotranspiration measurement at night. So this camera could be used actually for all these type of applications that you can see here, which are listed. And here is an example that we wanted to show about the land cover type recognition. On the left-hand side, you can see the radiance data. So basically, you have converted the digital numbers, the raw data of the camera into radians to give like a scale, which is in milliwatt over steradian per nanometers per an area, so square centimeters. And here, this is the spectra that you get. And here you could see the radiance data from a tree, sand, ice, and asphalt. Actually, this was flown at the top of Oulu, close to the beach in winter. That's why the sea is frozen, like now. And then, when you extract from the radiance actually the emissivity, meaning that you check what is the spectral differences with what will be a pure black body, then you can get the emissivity. Then you can see what is the emissivity, which is proper basically to the one of a tree, sand, ice, and asphalt. So here again, here you can see nice differences, and then you can identify those different type of land cover. That's it about the application. Then I'm going to speak about Specim offering for this spectral range, and I'm really glad to speak about this newcomer, the FX120. This is not new for us, this wavelength. In the past, we are used to have already the OWL, which was between 8 and 12, but then we decided to renew the product. So now we have a new one, the FX120, that we launched actually in December last year, in 2023. So this is the camera. The spectral range is between 7.7 to 12.3 micrometers. The amount of spatial pixels is much larger than what it was before. Now it is 616. So spectral sampling is about 30 nanometers, having 160 bands covering the full spectral range. So spectral resolution, full with half maximum, is 100 nanometer. The camera could be used in a fast frame rate, so we are talking here about 240 frames per second. The material of the detector, it's MCT based, and the output of the camera for interfacing is actually GigiVision Ethernet. The size, it's not that small, but it's not big either. It's about 25 by 30 by 22 centimeters for a weight of 15 kilos. What I would like to highlight, and you see it really well from the picture here as well, is that the lens is actually part of the camera here, because remember, this is a thermal camera, and it means the optics cannot be cooled down at 0 Kelvin, so it means that it has an emission, and in order to keep it constant, to keep the radiometric behavior of the camera constant over the time, the optics is also temperature stabilized. That's why it looks like this, like really well, how can I say, compact, with nothing really getting out, because it's because of the temperature stability like this that we want to keep constant. Different things, so as I said, temperature stabilized optics. The shutter is integrated, so when you are making hyperspectral measurements, as you know, you need to measure the dark reference as well as the white reference, but here's the dark reference, so here we have a shutter integrated. It has a keystone and smile, which is corrected, and unified spectral calibration between the device, which is what we call the building image correction, automatic image enhancement. As I said, part of it is actually the unified spectral calibration between units. You can set independently the spectral and the spatial binning depending on your need. Be aware it has an impact as well on the signal to noise ratio. The more you use binning, the more you can increase your SNR. On the other hand, you may lose some spatial and some spectral resolution, but you don't need to always have the best, the highest. So those things need to be considered depending on your application. It has a possibility to become somehow a multispectral camera. So if you are not interested to measure the full spectral range, you can select only some bands, which is what we call the multi-ROI. As I said already, this is a GigiVision standard interface. Flexible mounting as well location on the camera, so you can mount it by different places. It is a 16-bit data resolution for accurate detectability. There is also the possibility to make some remote firmware or software update, and then it's a ratchet instructor, so it could be used as well in harsh environment. Having the camera is one thing, but you need to use it, with our platform, because it's still a push-broom device, meaning it's a line scan device and each pixel of the line getting independent spectral information. We can use it on our Sisu Rock workstation, which is really dedicated for core logging imaging. In this station, up to 6 sensors could be used, meaning you can have different type of hyperspectral camera covering different spectral range, and also high resolution RGB, 3D mapper, things like this. We also have different accessories, like for instance here the lab scanner 100 by 50. Here you can see the latest device, hyperspectral camera from Specim. This is the FX120. This camera is also a push-broom camera, like all the devices from Specim, and this one recording spectra between 7.7 and 12.3 micrometers. It records over a line, and it has 616 pixels per line. This camera is actually now mounted on the 100 by 50 scanner, so it is suitable to get samples as large as 100 by 50 centimeters, equipped with a thermal illumination, because this camera is part of the thermal world. And as you can see, this is the same illumination as we were using with the FX50 that you saw in the previous webinar. So this illumination is suitable to cover the spectral range 2.7, 12.3 micrometers. This full system is actually compatible with our software, Lumo Scanner, and our SDK. So you have the possibility to trigger the scanner and to acquire hyperspectral cube like this with our acquisition software, like this. You press the button, and like this, you have the sample, which are then moving under the camera, and line after line, you can acquire the spectral cube. Here we are having geological samples. This is typical application for this spectral range. We have geological core scan like this, smoothly under the camera. And here you can see appearing the false RGB image. Here we can see Lumo Scanner, our acquisition software. We just saw the white reference passing underneath. And here we can then see the geological core scan line by line. And as we can see already with the false RGB, already some details on the core can be separated. Now it is a way back. So the core is passing back underneath. And this is only a false RGB, not a classification. So only 3 bands have been allocated to the red, green, and blue for visualization. So here we can see a geological core, which has been acquired with the FX120. The data are here. There were also some stones at the top, and you can see really well we can go into the details of the minerals and also of the core. There is a possibility to make some selection, like this one. And we can see the spectrum. I need to fit it to view, like this. So here we can recognize nicely the spectrum of the quartz. And then here there could be some other ones some other spectra, like here. And then there is a possibility even of changing the location of the band to see the rocks differently. And we can move like this and see again the samples. And then we also have two types of mount. We have the one for airborne application. So basically it has a dual blackbody calibrator which is included. Why is that? It's because when you are using this camera to obtain radiance data, we do not provide radiometric calibration as we do for the other camera between 400 and 2500 nanometers, but we have the possibility to somehow make a new radiometric calibration for each data acquisition by adding two black bodies in front of the camera like this. Why? Because the radiometric calibration will vary depending on the temperature of the optics. So here it can be taken into account. Anyway, so we have this mount. Be aware that this camera is not an ISA product, is not like an airborne product as such. We sell it as a spectral camera, but if you want to use it as an airborne product, then case by case we can discuss with you. And then you also have the possibility to mount it like this on a tripod, having the possibility to use it on the field like this, also with a dual black body. I was mentioning already about the illumination, that with this spectral range you cannot use the one you are using, for example, between 400 and 2500 nanometers. You cannot use LEDs, you cannot use really halogen. So here we have the thermal illumination. It is exactly the same one as we are using as well with the FX50. That was part of the previous webinar with the mid-wave infrared. So here we have those two radiators which are emitting following the blackbody radiation curves, following, you know, like the emission of a blackbody at about 900 Kelvin. And as you can see, you have some emission actually between, let's say, 2.7 and also more than 12 micrometers. So it's covering the full spectral range for our thermal camera, meaning FX50 and also FX120. So we have this illumination. That is the one we recommend to use when you want to work in reflectance. If you want to work on the field, you have this possibility as well, but be aware that with the solar illumination, you have the possibility to work as well. You can see it here. You have like actually good sun atmospheric transmission between 8 and 12 micrometers. Even so, you have a strong ozone absorption at the middle of the spectral range, but still. That's why the camera could be used as well in reflectance somehow when you fly under daylight. Okay, so why do you want to use hyperspectral imaging? This is non-invasive and non-destructive. This is really like contactless method to measure something. It can replace manual and visual inspection because here you really have sensors to give you something which is objective, not subjectives. Replace time-consuming lab test because if you want to make some spectroscopy, you don't need to have many sample points. Think about it, the camera can make an image and each pixel you can get spectral information. You can make also some real-time inspections. Cover 100% of the product stream, so that means here you have a full image, not only part of your system, or you don't need to take sample to measure them at line, to then make the analysis. Improve the chemical grading, because with this camera you can really see accurately and quantify accurately what you have, which characteristics you want to map in your samples. Close to 100% accuracy, so that means this time you can really check 100% of your samples. Detect a range of characteristics simultaneously. So if I take, for example, the meat industry, so here you have the possibility with a single image to look, for example, at the moisture, the proteins, the fat content, and different types of parameters. And you have a large amount of applications. The one I was mentioning before was only like the most common one, but feel free to use your imagination to find some new ones. If you want to contact us, if you want to measure samples or us to measure samples for you, or if you want us to make a demo, or if you need to have a quote, please do not hesitate to go to our website, Specim.com, or you can then send an email, info@Specim.com. All right, this one was the last session of all this journey through the wavelengths, like this, starting from 400 up to actually the mid-wave infrared, the 5.3 micrometers. If you missed one of the previous sessions, you can go to our website again, and here you can see the previous session, the previous webinar. I'm really happy to be here with you for this last one. So now, if you have any question, I will answer to it. Thank you very much. The Q&A session will start now. Hello everyone. So we are back here for your questions. And actually I'm happy to see that we got already some questions. So that's good. If you want to ask more, please don't be shy. Just put your question in the chat and then I will go through. So I will try to go through one by one and I will do my best not to forget anyone. So if I do, I apologize already about it. So let's go in order. First one. Is it possible to detect temperature till 1700 degrees? Where is our limitation? So that's an interesting question. When you want to measure temperature in general with hyperspectral camera, how to do that? So you know you have your sample which has a certain temperature, will have a certain emission. If your sample will behave like a black body, it will emit as a black body will do following the Planck emission curve of a black body, like this. So then you know that you have a peak of emission, and the peak of emission actually depends on the temperature of your black body. Actually, this is following the Wien displacement law for this kind of thing. So here, when you get a sample which is warmer, typically the peak of emission of radiance will be actually at lower wavelengths towards the visible. Now we have the long wave infrared, so we are more toward like longer wavelengths. So this camera will be more suitable actually to detect the peak of emission of a black body to a temperature which is lower. So when you have a black body which is actually warmer, you don't detect the peak of emission anymore, but you detect the height of the tail of the emission. And this is here what you can do, especially if you are 1700 degrees. I assume you mean Celsius, because typically the Planck curve is given in Kelvin. But for 1700 degrees Celsius, I would say that you have more like the peak of emission, which is close to be more in the visible. I don't know exactly the wavelength just like this, but I will put it maybe closer to 800 or 700 nanometers. So for this type of temperature, I would use actually a camera which is not the owl, even if it can still do. But if I want to detect the peak of emission, I would use a camera which is more like VNIR or NIR. So the way to do it, basically you need to convert the raw data into radians to see the spectral emission of your body. And here, remember that I was talking only about black body, so this is a model. It means that your sample will not emit exactly as a black body, but you have to model it with something. So that's why I was talking about the black body. But 1700 degrees, you can still do it, but you will not detect the peak of emission, which is the most accurate way, like this, of monitoring temperature. Pharmaceutic formulation, like solid tablet, any use case? Well, for tablets, I would use another wavelength. I would use either FX17 between 900 and 1700 nanometers or between 1000 and 2500 nanometers. This is actually where the active principal ingredient and the excipients, they have most of their spectral features. And for identification and quantification, that will be actually better than the FX120. How does the signal-to-noise ratio performance compare with the OWL instrument? So here we have someone who knows about the previous version of our camera for this long-wave infrared, for this spectral range. This is true. We had in the past the OWL, and now this is a replacement camera. We are having the FX120. In terms of signal-to-noise ratios, the FX120 is slightly better. So it's good, and you could see actually from the video, like the spectra, they were beautiful. You saw the image, they were actually really beautiful as well when it was passing like this under the camera, like the false RGB. So in terms of SNR, we have made some improvements. So the detector has a better characteristic in that respect. Pharmaceutical tablets uniformity of content testing with the technology combined with image analysis can be helpful. Yes, if you want to see the uniformity and if you want to detect, if you want to make some analysis with tablets, You need to have the hyperspectral camera, the one I was mentioning, FX17 or the SWIR between 1000 and 2500 nanometers. And here you need to have an image processing software. And here comes actually what we have, which is the Insight software, which is the software actually I was showing in the video. Like this is our Specim software for opening the data and also exploring your data and making model qualitative and quantitative. And it comes to the next question. HSI is using just for surface application, so we cannot see quantitatively the amount of active material in the painkiller tablet, for example. Is it correct? You're right. Hyperspectral imaging is a surface inspection method, so you cannot really see through. It has a bit of penetration depth, but still. So if you have a painkiller and you have a coating at the top of it, you are right, you cannot make any quantitative analysis, neither qualitative, because basically you will see only the coatings. But for many pills, actually, what you have at the surface is representative of what you have inside, because the way the pills are made, you know, they are well mixed, ingredients, excipients, so, and then you have your pills, you have the tablets. So you have to make assumptions that what you have at the surface of your tablet is representative of what you have inside. Some of them, they could be inside, you know, like something made kind of gelatin or something like this. And here, this is transparent to the NIR, so you can see through. Cool. Okay, so here we have this question. Could you use, instead of camera and spectrograph, a sensor for specific application to speed up the detection in industrial environment? So what you are telling me is, like, for example, you don't need to have a hyperspectral camera, but you could have a multispectral camera which is dedicated to some bands so that actually you can focus on those bands for your application, and then it makes the processing faster. You could do that. But if you think about some application, you may need to have many bands to be able to actually do the things, to do the work. So if you need to have many bands, at the end of the day, a multispectral camera is not much cheaper than a hyperspectral camera. And remember that with our FX camera, FX10, FX17, FX50, and FX120, you have the possibility to select only the band you are interested in. So basically, the hyperspectral camera could become multispectral camera, and then I agree with you, the fact of selecting some bands can make the acquisition, first of all, faster, but also the processing. What is the operation temperature of the sensor and the lifetime of the cooler? So the operating temperature of the sensor, it is +5, +40 degrees, like all our cameras. This is like how they are used. For the lifetime of the cooler, I have to say I don't have it just now in my mind. If I check the data sheet, I'm not sure it's written. So it's something actually, the lifetime, this is true. It has a Stirling cooler for the detector. So here, if you want more information about the lifetime of the cooler, please send an email to info@specim.com, and then we will come back to you. I just don't have the number in my mind. Sorry for that. Can the cooler be replaced in the field, or is the camera need to be sent to Specim for cooler maintenance? It needs to be sent back to Specim. This is not something you can do yourself on the field. You cannot just open the camera, disassemble, because you need to take the detector away. So to take the detector away and also to take the cooler away and then to reassemble everything, this is something that needs to be done at Specim. Can we expect some pharmaceutical tablet uniformity test case study? Well, actually, if you go to our website, there is like a blog, and there we actually put some different like case studies. And we have some dedicated to pharmaceutics application for tablet inspection, powder inspection, and things like this. So really, go to our website, specim.com, and there is a small research menu. If you type pharmaceutics, for example, then you will have different articles which could match actually your request. What will be the threshold detecting talc in rocks? Grain size or maybe percentage in pixels? Well, here I have to say I don't know how reactive is your talc, and I think it depends as well what you have within the context, which is the type of the rock. But what we have seen is that you can start to see the influence on a spectra when you have about 25% of a pixel which is covered, you know, with a mineral or with whatever is interesting. We have seen that, for example, for contaminant detection. We have seen that in a remote sensing application, you know, when there was like a contaminant somehow on the pixels. So here this is something we have observed, like 25% you can have something. But again, it depends how reactive is the talc compared to the other material. So if the talc has a spectral signature which is very different from the other materials, then you don't need to have like a high percentage to be able to detect it. But if the signature is similar and so on, so that might be another story. How will one choose this camera over a non-hyperspectral long-wave infrared? Well, here you're asking the question basically not only for the long-wave infrared, but why to choose a hyperspectral camera compared to another one? Because it doesn't matter if it is long-wave infrared or something else. The hyperspectral camera measures spectra. So this is what it does actually. So with another camera, you don't measure spectra. You may measure intensity globally, broadband, over like a region, you get an image, but you do not measure spectra. With the spectra, you have the possibility to identify different type of minerals, different type of active principal ingredient, different type of, you know, different type of things. But with a normal camera, a broadband, you don't have this possibility. I have done this question already. For the reference white and dark, is it automatically taken? You can, or you can disable it. In our acquisition software, you have the possibility to adjust the workflow, and in the workflow, you can choose to acquire or not the white and the dark. So it can be taken or not. It's up to you. Are there interesting applications for recycling industry? Yes, but not with this camera. For the recycling industry, we are using more like the NIR spectral range between 900 and 1700 nanometers. This is better for like cardboard, paper, different type of plastics. And also the FX50, if you want to separate black plastic, black but also non-black, but as soon as you are putting black plastic, you need to have the FX50. And we have actually sold many of those cameras for this type of application. So recycling is actually really important. You mentioned in the webinar that for aerial geological application, if there is vegetation, you will have some limitation to identify the mineral or to have a mineral map. Could you please elaborate on that? Is there a way to overcome this limitation? Yes, hyperspectral imaging is a surface measurement method. So you can see only what you have at the surface. So if you have vegetation or whatever it is at the top of what you want to map, like rock or soil or things like this, then you will see the surface which is at the top. So basically you will have something between the camera and the samples and you cannot get rid of it. Remember, hyperspectral imaging is a surface inspection method. How to overcome that? I don't really have a solution unless you are making some drill core, like if you are taking some samples like this, but then it's not aerial mapping anymore. But this is something you have to take into account. When you have cover, then you don't see what you have underneath. How humidity or wet samples will affect detection of minerals. Typically, when you are making like drill core analysis, the samples, they are dry. So to be sure not to have any effect of the water, which will have like an effect, of course, on the detectability of the mineral, we recommend always to have the sample to be dry. I haven't tested myself what happens if they are wet, but to the best of my knowledge, water will have still some absorption within this spectral range. So if the water is, and it's not if, since the water is having spectral absorption, it will act as a mask, and it is not recommended. Can you share some paper on pharmaceutical tablet content uniformity? Please go to our website, as I was explaining. And if you don't find there what you need, you can then contact us at info@specim.com. Can you improve the signal-to-noise ratio by slower scanning? If so, how much improvement? Actually, yes, you can do that. And this is a strategy we are using, for instance, with the FX50, but you can use it with that one as well. So basically, you cannot have integration time which is too long with this camera. And with the FX50, it's the same because it is a thermal camera. Because if your integration time is too long, basically you are filling the dynamic range of the detector with somehow with some noise, like you integrate optics and things like this. So you are not interested in that. So you are kind of limited with integration time. So in order to improve the SNR, you cannot put it too high. So what you do, you have an integration time which is decent, about 1 millisecond or something like this, up to 2 milliseconds. And then you scan on the field, but too slow. And sometimes what we do, we scan actually 20 times too slow, and then we make an averaging, a spatial averaging of the frame to put them together, and doing this average can then improve the SNR. So this is something actually it can be done, and we do it, and it helps a lot. Can you step a NEP value for the case of 240 Hertz and no binning? I think it is not NEP, but I think it was mostly NER, like noise equivalence radians. And I don't have the number here, but this is a question we can answer. So please drop an email at info@specim.com. Do we have more questions here? No, but we still have time. So please, if you want to know more about it, please move forward with it. You can put them. I have seen that we have, could we have your email for more questions? info@specim.com. Then it will be directed towards the right person. Yes, exactly. Thank you, Harry, who is just behind there. So then we will answer to you. Yeah, I saw we had quite a lot of questions about recycling and pharmaceutics. So really, this is not the correct spectral range for that. This is more like between 900 and 1700 and between 1000 and 2500 nanometers. So those are the best fit spectral range. Here, the long wave infrared is more like you saw the application, geology, military, things like this, or temperature. Do you have any application using any of hyperspectral camera for a bruise on fruit? Yes, actually this is an application that some of our customers have been working on. Take an apple, for example. When it falls down or when it freezes, the water basically, which is inside the cells, are migrating outside of the cell somehow, and then you have like, it's not the same combination. So basically you need to have a camera which is able to detect that, and we have for that actually the FX17 or the SWIR camera, but already with the FX17 you can do that. Why this camera? Because with this camera you can have a penetration depth which is actually deeper than with the VNIR camera, which is between 400 and 1000 nanometers. So you can see behind the skin somehow of the fruit. So if you have an apple, you can see through the skin. If you have a strawberry, you can see behind the skin as well. And there you can detect basically if you have a bruise or not. And I have seen research on kiwis, tomatoes, apples, strawberries. Yeah, those are the ones I have seen, but there might be some other ones as well. And I see that actually Harry has been sending the link for this. Do you have any more questions? Have you developed a camera in UV range? In the past, when I started at Specim more than 10 years ago, we had a UV camera. And we don't have it anymore because there was no demand, not enough, like so. So we stopped it, but we had it. You have to think like with UV, you have to be careful. For example, with a light source, this is not something which is very simple. You need to have a UV light source, and you have to protect your operator, because with UV light source, you will burn your operator, like the skin. So you should be careful with that. And also, many people sometimes when they say they want to have a UV hyperspectral camera, actually they don't need a UV hyperspectral camera because they are doing fluorescence at the end of the day. So they have a UV light source, which is at, let's say, 365 nanometers, and then they want to see the emitted signal, the fluorescent signal, which is then in the visible part of the spectrum. So then we have the FX10 for this visible part of the spectrum. But if you think about UV hyperspectral camera, meaning you have a light between 200 and 400 nanometers, for example, and then you want to see the reflected signal between 200 and 400 nanometers, no, unfortunately, we don't have it anymore. Yes, but we had an issue where the camera is unable to see bruises in a fruit which has a thick skin, like for example, pineapple. What do you reckon? What we can do? Yes, I agree. If you have like thick skin, if you think about banana, if you think about pineapple, I have made some try. I don't know, yeah, but maybe it was more like, not for the bruise, maybe it was like for the sugar content and things like this. But if you think about oranges, if you think about like, yeah, citrus, lemon, things like this, I agree with you. When you have a skin which is too thick, you cannot see through. And yeah, here the technology is not suitable for that. Okay, so any more question? I wait still, maybe 1 minute, half a minute. Maybe 1 minute, being quiet is a bit long. So I think, well, maybe we can conclude already here then. We got one. No, please write yes to the chat if you want our sales team to contact you. Okay. So I think I can conclude here for this session. I would like to thank everyone again for attending this webinar. Again, we will see you again to the next one. It's just that this series is over, but I'm sure there will be a next webinar coming soon. Actually, I don't know when yet. We are still in the planning phase, but there will be one coming. Thank you very much. I wish you to have a nice day. Don't forget to go to our website, to contact us. We'll be happy to come back to you. And yes, so see you. Reflection from man-made objects have different polarization signatures than natural objects. Can you comment on use of your camera together with a linear polarizer for improved detection of man-made objects? Our cameras are free of polarization. So basically, you can choose to put a polarizer in front of it. And for most of our lenses, actually, there is a mounting thread. So you can put filters, so polarizer or like a neutral filter, things like this. So you can put some. It is used a lot, especially in geology, for instance, like polarization is important there as well. Also to get rid of specular reflection. Some people, they use polarizer because specular reflection is actually highly polarized. So yes, we have people who are using actually the polarizer to put in front of the camera to get rid or to see, to enhance or to get rid some of the signals. Great presentation, thank you. Besides geological drill cores, the scanning table could be used to scan large fossil examples, sculpture and painting, for example. Yes, I agree. Here, this is a large table for the Ciso rock, but we also have the one of the 100 by 50 scanner, and you can put whatever sample you want to measure, basically. So it can be large, small, big. So to give an example, once on a Ciso rock, we actually measured a policeman. There was a man laying down like this on the Ciso rock, and the idea was to actually, he was shooting with a gun, and they wanted to measure the residue of the burned gunpowder on his hands. So yes, we have measured a lot of different things, paintings, sculptures, and the big scanner could be used for that purpose. And I must admit that our cameras are used quite extensively as well for art research, since you mentioned about like sculpture, painting, or like some other thing, yes, for those scanner could be used for that purpose as well. What type of sensor is inside the FX120? It's not a bolometer. No, actually it is a MCT. It is a MCT. In the past we had another camera which was based on bolometer, but you had issue with the bolometer in terms of sensitivity, in terms of adjusting integration time, frame rate, and so on. So here with that one, we are using a MCT. Is it possible to use multiple cameras with the same samples and extend the wavelength range in a final combined image? Yes, you can do that. So for instance, with the Ciso rock, you heard me, you can put many cameras at the same time, up to 6. And here you have the possibility to put them all after each other. And by one scan, each of the camera can record to its corresponding wavelength. So yes, then you can have like one cube obtained with one spectral range, another cube obtained with another spectral range, and so on. you will not get a pure fusion of having the full spectral range. So you will have individual cube for each camera. But yes, you can do that. Great talk again, so thank you. If I was to put object longer than 1 meter on the table, on the lab scanner, will it just stop recording when it's reached 1 meter? Or is it impossible to put longer object? Well, actually, on the 100 by 50 scanner, if you think about that scanner, you can put objects which are slightly longer. So for instance, the table is up to 1 meter, but it can measure a little bit what you are over. So I have been measuring sometimes samples which were like 1.2 meter or something like this. But there will be a point that you cannot move indefinitely like this. It depends on the length of the translation stage, which is actually underneath. So 1 meter is not a hard limit, but don't go to 1.5 meters. That will be a bit too much. In measuring temperature anomalies, what sort of resolution is possible? You mean in temperature-wise? That's a good question because actually it depends on the temperature you are talking about. Because you know, like when you want to measure temperature, you actually convert the data into radians, and then from the radians you try to find a match with what will be the perfect emission from a black body with a similar temperature, and then you see the Planck's emission curve. So you know that when you have a Planck emission curve, you have a maximum, and the maximum of emission. And this maximum of emission, by the way, depends on the temperature. This is the Wien's displacement law. Sorry, I have issues to say it. So here, if you want to be the most accurate, it's always good to try to find where you have this maximum of emission, because that's easy somehow to map, to detect. So if you are in a temperature range that you can detect it, you can be very accurate. If you are not on it, so for example, if you have a sample which is really warm, and then you have like a camera which is for the longer wavelength, you see only the tail like this of this emission. So of course, depending on the temperature, the level of the tail will be higher or lower. But anyway, so here you will be less accurate as if you will be able to measure like this the peak of emission. So depending on the temperature you are looking at, you should take a camera which is the most suitable for that. And then you need to link it basically with the signal to noise ratio of the camera. Then you can be more or less accurate with the temperature you are measuring. So it's difficult to give a definite answer, but you could see, for example, on the graph that I was showing, like during the presentation, it was pretty accurate. I would say 1 degree, but again, it's hard to give a hard number. It really depends on the temperature range you are talking about and the spectral range of the camera. Okay, so I have the question. So this one. Is camera able to detect fault inside aluminum profile? So you mean like if you have an aluminum profile and then you have some cracks or something like this, I can imagine. So that's what I understand from the question. Maybe I misunderstand, but I will try to answer that, what I understand from the question. Well, those cracks, for example, they could be more like morphological. It's not something which is more like chemical defect. So here basically I will recommend to use another type of sensor, for example a high resolution RGB camera. So here you can see really fine defects which are more like cracks or things like this. Maybe your question raises another point. You say to detect fault inside aluminum profile. Remember that hyperspectral imaging is a surface measurement method. So when you say inside, I'm not sure actually like no, you cannot see through the material unless it is transparent to the wavelengths, but typically it is very a surface measurement method. I'm looking for application in detecting foreign bodies in food manufacturing. Can the unit be enclosed in a hygienic enclosure? We have harsh and wet condition. Yes, actually, well, it's another spectral range. When you want to detect like contaminants in food, it could be more like between 400 and 1000 nanometers, or between 900 and 1700 nanometers. So here I actually invite you to check the previous webinar we did about those wavelengths. So one corresponds to the FX10, 400,000 nanometers, and then the FX17 between 900 and 1700 nanometers. And then those cameras can indeed detect different types of defect, contaminant, and things like this. About your question, Yes, we have the possibility to have a casing. Actually, you should go to our website in the accessories. It is mentioned, and actually Harry is telling me, I mentioned already about this one. Yes, it is actually mentioned. It is called the chameleon for FX enclosure. So here, yes, we have a casing, and it is food graded. So it means that it could be used for the food industry, and it is, sorry, with and without temperature stabilization, depending on your environment. Okay, the next question. Eventually, thermal illumination could damage any type of material. That's interesting because here you are right, you are in the thermal range and the illumination, as you saw, is slightly different. It's not based on halogen, it's not based on LEDs and things like this. Think about it. If you use halogen, halogen is not cold at all, neither. So, you know, a typical illumination for hyperspectral imaging could be the halogen lamp. So here you have to be careful on the heat. If you want to be careful with the heat, then you need to use some different spectral range, illumination for different spectral range. So if you can get rid of the halogen and you can use LEDs, for example, that you can find, for instance, between 400 and I would say 1700 nanometers, then you could use that, then you will not damage your sample. We have made some tests, for instance, with our 100 by 50 scanner and the thermal illumination that you have seen here. Remember, we are making line scan device and you need to have a scanner, you need to have a movement. And here we made a piece of art under the thermal illumination and it was moving at about 10 centimeters per second and it moves one way and then on the way back. And we measured that the piece of art, the temperature was rising by about 4 degrees and 7 degrees with the way back. So that means that you could damage your sample, but still the camera is pretty fast, so the movement of the scanner could be pretty fast. So in that respect, you will not damage your sample. Has anyone investigating using the system in a manner similar to spatially offset Raman? Oh, I'm not sure to know what is a spatially offset Raman. What I can say is that typically with a Raman you need to have a laser excitation and then you see what is basically the emission at different wavelengths as the laser excitation. Some of our spectrograph, in the past we sell them, they were like Raman spectrographs, so the camera could be used actually to see the emitting signal from a line like this. So we had actually a Raman spectrograph for making a Raman hyperspectral camera. So this is what I can answer to this question. Any more question? Maybe I can speak about question because you know you are the evening session for me, and this morning, my morning session, we had some more questions, for example, about geological application. There was a question asking if you want to use the camera for airborne, do you have the possibility actually to make soil mapping even if you have vegetation cover? And here I would like to highlight that it is not possible because you know hyperspectral imaging is a surface inspection method. So if you have a cover at the top of your sample and you cannot see through, so then basically you are limited. So keep in mind that this is a surface inspection method and really that's something really to keep in mind. I said that the lens is fixed to the camera to control the thermal emission. It is inside the casing of the camera. Will I have to control for the temperature emission of all things that I put in the optical path, like mirror, polarization, filter, and protective glass? Yes, it is true. So because if during the measurement you have things which are on the optical path, basically its own emission will change during the measurement. So when you take actually a reference, which is like what we call the cold reference or the dark reference, you have to take into account, you have to make the assumption that the temperature, the emission of those instruments basically will actually have an effect. So yes, you need to stabilize them. Another thing is actually interesting to think about when you want to measure a sample indoor in emission. If you actually have the sample which is at the same temperature as the wall and the ceiling and everything, you will have reflections on everything that you have around. That's the funny part with the thermal world. So here, basically, when you want to measure a sample at emission indoor, either the sample has to be colder or warmer than actually all the surrounding. If you're outside, it's different because then you don't have reflection from the walls the same way. Anybody else? Any other questions? I can wait a little bit to see if someone wants to say something else. Let's see. I can only say that here, this webinar, actually, you will have the possibility to get like the slides. All right, so if we don't have more questions, maybe I can just conclude. Okay, so I will conclude here. I would like to thank everyone to take part to this webinar, to attend, to look at it. And I hope you enjoy actually this series of webinars, which started already, I don't remember last year, maybe in September, I don't remember exactly when, but when we started the journey for all the spectral bands. So this one was the last one of the series. That doesn't mean that it's not the last webinar. I'm sure there will be some other ones. I don't know exactly when yet, but so we will be glad to see you there again for the next one. I wish you to have a nice day, a nice evening, and see you to the next time. Again, thanks a lot for your participation here. Bye-bye.